Hi, in this video we will look at the trends and patterns in some of the physical properties of the alkali metals. We will also have a look at the reactions of the alkali metals with water, halogens and oxygen. Now if you need any more help with any of the topics in this video, then click the links in the description below. Group 1 in the periodic table contains a rather unusual group of very reactive metals called the alkali metals. These metals are lithium, sodium, potassium, rubidium, cesium and francium. Now most people would probably imagine metals as hard, dense, shiny solids with high melting and boiling points and as substances which are good conductors of heat and electricity. Now while group 1 metals do have some of these properties, for example, they are shiny when freshly cut with a knife and they are good conductors of heat and electricity, they also have some very unusual properties for metals. For example, they are all soft and can be readily cut with a knife. Lithium at the top of the group is the hardest of the alkali metals, and the metals become softer and easier to cut as you descend group 1. The melting points of the alkali metals are also not what you might expect of a metal. For example, lithium melts at 180 degrees Celsius, sodium has a melting point of 98, potassium 63.5, rubidium 39 degrees Celsius and cesium 28 degrees Celsius. When you compare it with other metals such as silver, which melts at 962 degrees Celsius, or iron, which melts at 1538 degrees Celsius, or even gold, which melts at 1064 degrees Celsius, you can see that the melting points of the alkali metals are very low in comparison to what most people would expect of a metal. But perhaps the main difference between alkali metals and other metals in the periodic table is their chemical reactivities. The alkali metals are all very reactive metals. Now they are stored in jars full of oil or paraffin to keep water and oxygen away from them. These metals react very violently with water, and it is essential that they are stored under paraffin or oil. There are a few easily identifiable trends and patterns in some of the physical properties of the alkali metals. We saw earlier, for example, that the melting point of the alkali metals decrease as we descend group 1 of the periodic table, and that the melting points of the alkali metals were much lower than that of other metals found in the periodic table. A similar pattern is found in the boiling points of the alkali metals, in that they all drop as we descend group 1. The densities of the alkali metals show the opposite trend, in that they increase as you descend the group, but however the density for sodium doesn't appear to fit this pattern. Now recall that the density of water is 1 gram per cubic centimetre, so this means that lithium and sodium potassium all have densities below this value, so they will all float in water, a bit unusual for a metal. However, the densities of the alkali metals are still much lower than that of a typical metal. The image shown on screen shows the densities of some common metals, and you can clearly see that the densities of these metals are still much higher than that of any alkali metal. Now group 1 in the periodic table is called the alkali metals, simply because they react with water to form alkaline solutions, that is, solutions of metal hydroxides. Equations for the reactions of the first 3 alkali metals with water are shown. You can see from the equations that the alkali metals all react with water to form alkaline solutions, that is, solutions of metal hydroxides, and that the flammable gas hydrogen is also released. The animation shown highlights the typical reactions of lithium, sodium and potassium with water. Now enough heat is generated in these reactions with the water that the alkali metal will actually melt to form a ball of molten liquid metal that shoots across the surface of the water. The reaction of water with potassium is so violent that the hydrogen gas will actually ignite by itself and burn with a mauve or light purple coloured flame. Sodium and lithium react less violently, and the hydrogen produced here will not ignite or burn by itself, but it can be lit with a burning splint. However, once the gas is lit, it will continue to burn on its own. Sodium metal will colour the flame yellow, while lithium will colour the flame a brick red colour. If an indicator such as universal indicator is added to the trough of water, it will slowly turn purple during the reaction, showing that the solution produced is a strong alkali. Now, the general trend in the reactions of the alkali metals is that they become more violent as you descend the group. The reactions of rubidium and cesium with water, which are not shown in the animation, could be best described as explosive reactions. Recall that chemical reactions of any particular element depends on the number of electrons in the outer shell, and since the alkali metals are all in group 1 of the periodic table, they will all have 1 electron in their outer shell, which they will lose when they react, and this will explain why they react in a similar way. Now, as you move from lithium to sodium to potassium and so on down group 1, we simply add 1 more electron shell. This means that the atoms will be getting bigger, and since the inner shell electrons also screen or shield the outer shell electron from the nucleus, this means that the outer shell electron is further away and will be screened, so will require less energy to be removed, meaning that the alkali metals become more reactive as you descend group 1. The alkali metals react with the halogens, fluorine, chlorine, bromine and iodine to form colourless ionic solids. Now, these reactions are very exothermic and can also be very violent. The reactions would follow the expected trends, that is, the more reactive the alkali metal and the more reactive the halogen, the more violent and explosive the reaction is likely to be. For example, the image shown shows a possible setup for the reaction of the alkali metal sodium with chlorine gas. A small sample of sodium is placed on a mound of sand in the base of a flask. The flask is then filled with dry chlorine gas. To start the reaction, a single drop of water is placed onto the top of the sodium metal from a pipette. A very violent reaction occurs between the sodium and chlorine, and a bright flash is seen as the sodium and chlorine react. The flask quickly fills up with white smoke, which is actually solid sodium chloride. We can show the reaction using the following word and symbolic equations, and it can be summarised in general using the equations shown on screen, where M is any alkali metal and X is a halogen. The products of the reaction of an alkali metal with oxygen depend upon the reactivity of the particular alkali metal. A mixture of different oxides can be formed depending on how reactive the alkali metal being burned is. Now, the possible products for the combustion of an alkali metal are a metal oxide, a metal peroxide and a metal superoxide. So, for example, if a small piece of the alkali metal lithium, the least reactive alkali metal, is placed on a burning spoon and heated with a Bunsen burner, a brick red coloured flame will be seen as the lithium metal burns. Now, when lithium burns, it simply forms lithium oxide. A word and symbolic equation are shown for these two oxidation reactions. If you need help working out formulas, then click the links in the description below. Now, if a small piece of sodium is placed on the burning spoon, it will burn with a yellow flame to form 2 oxides this time. One of the oxides will be sodium oxide and the other will be sodium peroxide. And as before, a word and symbolic equations are shown for the production of these 2 oxides of sodium. Finally, if a piece of potassium is placed on the burning spoon, a lilac coloured flame will be seen above the molten metal. Reactive alkali metals such as potassium, when they are burned, will form a metal peroxide and a metal superoxide. Equations for the formation of potassium peroxide and potassium superoxide are shown. Now, you don't need to be able to explain why these different types of oxides are formed with different alkali metals. You just need to remember which alkali metal forms which type of oxide.